We're going to approximate a definite integral using Simpson's method. So we have our function that we've been working with and the integral under consideration. And we're going to do two subintervals. So the idea behind Simpson's method is that we fit the endpoints and the midpoint of each subinterval with a second degree quadratic polynomial. In other words, a parabola. Then we find the integral of each polynomial over its subinterval and add those numbers up. So we're only going to use two subintervals so we can do this. So the idea is over here. Here is the original curve in red. Then over the first subinterval, which is 1 to 3, we have the endpoint and the midpoint, which is 2. And we get those 3 points, these three. Then we fit that with a polynomial, and there are several ways we're going to go over on how to do that, and we're going to have that on homework problems. So the blue is the parabola fit, and it would come through here, keep going. It'd probably come out here and do something like that. But I'm just cutting it off from 1 to 3. Then over the second subinterval, which is here and here, then we fit the left and the right endpoint of that and the midpoint to get this point. And we fit that with its own parabola. And that would be this green one that's really hugging it close on 4 over x. It's not 4 over x, but it looks very close. It probably diverges over here. And then we just get the integral areas under each of those parabolas, and that's your approximation. You can see that this second subinterval area is very, very close, and the first one has a little bit of overage and a little bit of under. So this is going to be a really good approximation technique because we've only done 2 subintervals so far, and already you can see that the areas are going to match up. Okay, let's find out how to get those parabolas. First method, go to Wolfram Alpha and put in Lagrange poly. That's for Lagrange interpolating polynomial. Put a set bracket, put the 3 points you're trying to fit in there with commas. For example, on the first subinterval of our particular problem, we have 1, 4, 2, 2, and for some reason Wolfram Alpha likes this to be a decimal, so give it a nice decimal approximation there. For instead of 4/3, it's this. Okay, and then press the equal sign, and you're going to get the polynomial that way. And I'll show the example of that in a second. The second method is to use Simpson. It's like this kind of a method, kind of looks like a kind of a midpoint method or a trapezoid method. Actually, it's really a combination of those, and it can be proven that this is the exact same answer as the first method, and we're going to have a problem that does that. The third method uses a weighted average of 2 midpoints plus a trapezoid all divided by 3. That's the simplest. Well, if you know you have to compute the midpoint of trapezoid first, but that's, once you have those, that's the simplest to get Simpson. And that's exact. 4, the same as 1, getting the parabolas, except this time don't use Wolfram alpha. Instead, use the 3 points and get 3 equations from that, solved by a matrix method or Gaussian elimination, or if you give up on that, go back to Wolfram alpha, and you get the A, B, and C, and they turn out to be, for this particular example, for this first subinterval, these 3. So your parabola for the first subinterval is going to be this one. Okay, now let's go over how to actually do each method. Method 1, use Wolfram alpha to get the interpolating polynomial, which is a parabola. Put in this syntax for the particular points you're trying to fit, just 3 points, determine a parabola. So it gives you it, and then you turn that into fractions that it should be. You can easily do that. And you can verify that the 3 original points satisfy that equation exactly. Then you integrate that on the first subinterval from 1 to 3, and you get 40/9. Then you do it again with the points fitting the second subinterval. That's these. Again, you get this decimal version. You change that into fractions, and it satisfies the 3 points. And you run the integral from the second subinterval, 3 to 5, on that polynomial, and you get 92/45. And when you add up those two integrals, you get this, which is then 292/45. That's the exact answer, which decimal equivalent comes out to this. And that is the answer to Simpson. Method 2 says to use this formula, and for some reason that's equivalent to the previous one. So we only have 2 intervals, thank goodness. So you figure out your delta x is 2, the function is 4 over x, and so using that formula, I took the delta x is equal to the 2, and you have the 1/6 over here, that's where that 6 came from. And I just followed the formula for the first subinterval and followed it for the second subinterval, factored out the 2/6 for each one, added all those numbers up, reduced the 2/6 down to 1/3, and sure enough it comes out exactly to 292/45. Again, the same answer as we got previously. Method 3. Method 3 says to do a weighted average of the midpoint, 2 midpoints plus 1 trapezoid, all divided by 3. So you have to figure out the trapezoid, but the simplest way to do the trapezoid is that it's the average of the left and right, which we have problems to do to prove that. And that gives you these fractions once you figure out the left and the right, and that adds up to 112/15. The midpoint is pretty simple. It's just the f at the average, the midpoint of the subinterval and the midpoint of the subinterval, and that comes out to be 6. So Simpson 2 says to do 2 midpoint with n equals 2 plus trapezoid with n equals 2 divided by 3. Put those in, and sure enough you get the exact same answer, 292/45, which checks out. Okay, method 4. Get your parabola for each subinterval by solving a system of equations, then integrate each of those over their subintervals. When I was talking about that was one of the possible methods, I showed how to do that. That's going to take a long time, but that's one of our homework problems. Method 5, run the integral program with n equals 2 steps, and watch for when Simpson comes up. That's the answer to Simpson. So you can verify your work using the integral program.